Happy Monday. I hope you guys are having a great day, enjoying being inside, not sweating, not going outside, the usual. Lily is not participating in class today. She really just said she was kind of done learning for the day. I don't really know. She was just like, and I'm out. So she is outside the room today, but she's in the thumbnail, and so she said to tell you all hello. So I hope you guys are all having a good week. I would tell you that I did something exciting this weekend, but I didn't. I stayed at home, watched a few shows, started Pandemic on Netflix, which is probably not the wisest idea. Been trying to find my Gen Chem students recommended Tiger Family, Tiger Life, Tiger something, and All American as new shows to stream. In this moment, we've got several going on, but since I can't leave the house, like for sure, that's what's going to happen next. Basically, Operation Watch TV for days is what's going to happen. I'm trying to think. There's something else that I've been running, but y'all, it was so hot in Florida this weekend that I pretty much was like, I'm going to die. I wasn't prepared. It's only March. Also, it makes it very difficult to stay in the house if everything you want to do is to be outside. Lily is, to be quite honest, so over this life. Sorry, I was trying to, there are my announcement slides. So today is Monday. I miss going to school. I hope all of you saw the email from the provost about changes to the grading policy. That changes some of the grades. It is an opt-in situation. So if you have questions about that, feel free to pop into office hours, or basically you can pop in to, I don't want to say other options, but you can come to office hours, or if you'd like, we can set up a private meeting if you have specific questions about that. Last Friday, I uploaded the scans of your exams. As far as I know, I didn't get any emails that said they weren't there. So let me know if some sort of technical who's-he what's-it has happened, because we all know that's totally possible. Hopefully you all saw that. There will be an assignment on Wednesday. For Wednesday, a series of Jove videos are going to be posted on campus. A new module called Molecular Cloning opened, which has some pages you can read out of the Appling textbook. Those page numbers correspond to the sections we're going to talk about. And then I will post in order a series of Jove videos. Mostly you need to watch the part that tells you about the technique, not necessarily I pipetted 1 microliter into this tube and then we set it here. I'm going to ask theory-based questions as opposed to questions about really specific entities. That sounds kind of crazy. For Jove articles, there are 2 ways that you can access that. I got an email from them today, so I may be updating the way that you can do this. But you can sign into the UNF library and then sign into Jove to watch these. I'm also going to attempt, and I've tried this a number of times and it does not really work, to make the video links in Canvas the type where you can auto get into that. Doesn't work very well. I can't seem to get that right. But you can make a Jove account that's free and they will just send you an email and you can watch any educational video you want. So I made an account so that I could access it from my house because I was having trouble accessing it from here. Sorry, I can hear my dog making like barfy sounds. apparently she's having a rough day. So for the remainder of today, actually, I guess we'll ask, does anyone have any questions about anything? We will be having a final in this course that will not be going away. If anything, there may be some slight adaptations to the amount of points in this course, but overall, it should be fine. Today, we are going to talk about chapter 19, which is the last chapter in Metabolism Bootcamp. Okay, come on. No, is this what she wants? She's fine. Y'all, dogs. Hey, Lil, this is what you'd like. Do you want to say hello to our students? Say hi. You want to say hi? Yeah, that's right. I'm sorry, she is just full of sass today. But we will give her a treat. Thank you for coming to class. Sorry. We're going to talk about chapter 19. If you have any questions about 17 or 18, you can access via Zoom my office hours. I updated the front page of our Canvas site to where when it tells you the office hour times, you can basically just click that link and go straight to office hours. It is it's a recurring space. So basically, if you click in there and it's during the workday and you hang out in there, I will likely pop in to be like, hello. Otherwise, I sit in my office hours and listen to music and do stuff on the computer. So you can come hang out and do all of that too. So let's talk about chapter 19. If no one else has any other questions. So for chapter 17, we talked about, so Metabolism Bootcamp is a little bit different than what it was in the first semester where you guys talked about glycolysis and the citric acid cycle and some of that. So in chapter 17, you talked about fuel metabolism. In chapter 18, we talked about amino acid and nitrogen metabolism. Today, we're going to talk about nucleotide metabolism. So it's important to think about, where do we get nucleotides, or where do the components that create nucleotides come from? So if you start, today we're going to start on it's a hard life. Slide 47. And so in slide 47, there are two different ways we can create nucleotides. De novo, which is Latin for anew, or salvage. So if you want to salvage something, you basically can reuse it, kind of like recycling. But so we can see DNTPs that are synthesized from the elements, nitrogen, carbon, oxygen, hydrogen, or it's a salvage pathway where but DNA and RNA are recycled to create new DNTPs. Likely, we will have to add back on phosphate groups to take them from the monophosphate back to the active triphosphates. So if we look on slide 47, we can see at the top, we can see a recycling of the nucleic acids to make oligonucleotides and to go around. On the bottom, we can see that the bases can be converted using uric acid or pyrimidines or other things in order to go around this cycle in any way, shape, form, or fashion. So let's look at slide 48. So nucleotide metabolism overview. We know that DNA and RNA are most of the times where we're going to see our nucleotides go. And so we need them to be active in DNTPs or other options. So one thing we'll start to see is that their precursors for some of them are going to be other amino acids that get combined with other carbon-based molecules to create complex ring sugars or complex rings. So on slide 49, purines. So purines, if we remember, it's the shorter word. It is the larger ring system. This is how I remember it 100% of the time. So purines require several amino acids as precursors. If you look in the lower left, I don't want to call it quadrant, but corner, we can see that to create a purine building block, we see aspartate, glutamine, and glycine. All three of those components and CO2 come together to create the single ring system. And so both of them are derived together. So PRPP, which is 5-phosphoribosyl AD1 pyrophosphate, or PRPP, works just fine, is an important intermediate in this synthesis. So if we look on the right side of the screen, we can see the ribose phosphate, and the ribose phosphate now adds in phosphate groups. And we know that the movement of phosphate groups is really energetically favorable. So we can see the PRPP is the intermediate that's going to add on the sugar and the phosphate groups. And then the phosphoribosyl transferase is going to use the movement of the phosphate groups in order to create the purine building blocks that we need. So in this case, the sugar component and the ring component are created separately and then joined back together with phosphoribosyl transferase. So they are not created together. So on slide 10, the de novo purine synthesis. Now, I know that for many of you, you're looking at this and you're asking yourself, is she going to make us memorize this? And the answer is no. Nope. You do not need to memorize this. You do not need to memorize any of the components. You do not need to memorize which enzymes do this, what the intermediates are. In Biochem 1, a lot of times during glycolysis, you have to write out like all of the intermediate steps. We're not going to do that. We are definitely not going to memorize this graphic. I feel like I've made you guys memorize a lot of things. This, not the thing that I think we need to know. So when we look at this, one of the things we can start to see if you look into it, is that it requires 10 reactions to go from inosine all the way to purate, or 10 reactions to form inosine monophosphate. So the purine ring is synthesized while attached to the ribose ring. So in this case, we start to see two different things. And so I know on the previous slide, it says that the purine ring is added later. But in this case, this is the de novo purine synthesis. So you can put them together later, or in this case, we can go ahead and look at this. And so one of the things to think about is it requires significant effort in order to create this. And so you can see that it adds one piece on at a time, often moving ATP or GTP. It's actually all ATP hydrolysis, as well as the formation of a couple of other things. So the purine ring under de novo synthesis is composed so different than salvage. So if we look at slide 51, ring diversity. So the reason we want to think about ring diversity is because there are two purines, and the question is, do you make two molecules that are the same? Or is it one pathway with two products, or two separate pathways? So it turns out that the inosine monophosphate is what we get at the end of the 10 steps for the de novo purine synthesis. That then undergoes an additional 2 steps, 2 to 2.5 steps, in order to create GMP or AMP. And so there are 2 other reactions on both sides. So realistically, you could almost count it as 4. So I'm on slide 51. And so we can see that for both of these, they require different pathways in order to get into the intermediate step. And so GMP and AMP are converted into a usable form of DNTPs later on down the road. So from here, we have AMP or GMP, and they're kind of in a waiting queue. So waiting queues are great, but not necessarily super helpful. So the next thing we want to think about on slide 52 is uric acid. So we talked about uric acid last class on Wednesday of last week. So uric acid is insoluble, and we talked about how uric acid, when we encounter that, it can be broken down to create urea, which is excreted through urine, or birds can create more of a solid uric acid deposit. But uric acid, either way, when you encounter that in the body, is insoluble. And so it can be converted into a soluble product of urea, water, obviously, and carbon dioxide and ammonia. So we can take our uric acid and break it down, or it becomes a solid component that is insoluble. So the animals that can excrete solid uric acid, but if we don't dissolve our solid uric acid, we're going to have uric acid buildup. So uric acid is a scavenger of free radicals. We know based on our conversations out of chapter 23 that free radicals can cause DNA damage. So having a free radical scavenger is not a bad thing, but the uric acid does need to be degraded. So the thing we kind of want to think about, and the reason we're thinking about uric acid, is because uric acid looks somewhat similarly to some of the other components that we saw is the end products for AMP and GMP. Not quite the same, but similar. So on slide 52, if you can't break down uric acid, you're going to start to get uric acid deposits. So you can get hyperuricemia, which is elevated levels of blood uric acid to the extent that it crystallizes in the joints. Now, as chemists, we know that the higher your concentration is in a given volume. So in this water, if I was pouring in salt, just straight up salt, a lot of it would go in solution and some of it would start to crystallize at the bottom. You can make a super saturated solution, which is definitely not what this is. It's just regular water, where once it starts to evaporate, all of the solid components come out. So we see that in inorganic with seed crystals, or in organic where we want to crystallize components. But here in the biological system, I don't really think about the ability to create crystals as being a good thing. So gout is, if we're looking at slide 53, we can see King Henry, I think the 8th, and Jared Leto. Now, Jared Leto has gout, which tells me that gout is not just a past disease, because he's still very current and very active. So in North America, 3 out of 1,000 suffer from gout. In the, not olden days, because that sounds like 8 months ago, but in the past, back in the 1400s, it was really thought to be a rich man's disease based on diets high in fat, alcoholic beverages, and other rich foods. So part of the issue is that gout, when it comes, it is that you have excess blood uric acid and it starts to crystallize. If you look at the image on slide 53 of the Okay, so we had some technical difficulties. So YouTube tells me that we're having tech difficulties, but doesn't really tell me when it's over. So I don't have any idea where we were when they started. But we'll go back to our gout discussion. So 1 in 3 in North America suffer from gout. And so if we think about where it's gout deposits or the uric acid deposits are located, it's often in joints, feet, ankles, fingers, toes, wrists, elbows. So in these joints, we start to get uric acid buildup. And as they build up, they get crystallized. The crystals cause pain. And so we know that those can occur. And the question becomes what happens and how do we get those? So if we go to slide 54, one of the leading causes of gout, which implies that there's more than one, is the deficiency of the purine salvage enzyme, hypoxanthine guanine phosphoribosyltransferase transferase. So basically what this is going to say is that if you have deficiency in the HPGRT, you are more likely to get gout. So basically, if you cannot salvage purines, then you're going to start to have buildup. So the treatments of gout are lifestyle changes. So one thing they have noticed is if you modify your diet, which is often true in a lot of what I would consider metabolite disorders. So when you think about diabetes, certain types of diabetes, not all, and in this case, gout, you can minimize the effects based on your components in this case. So you can also, there's a drug. So allopurinol is a suicide inhibitor. So if you look at the right side of slide 24, the allopurinol is a suicide inhibitor, and so it is on the lower components of this graphic. And so it's going to prevent these xanthine oxidase, and it's reversible and irreversible in different components. So a suicide inhibitor means that it will work one time, and basically it becomes a target and it turns that enzyme and turns it off. So in this case, if you can, it basically allows for a rebalance based on the suicide inhibition of other components. So basically, if you block one pathway, the body will use others. So that is one cause of gout. So that is a deficiency in this enzyme, which is treated both by drugs as well as lifestyle changes. So on slide 55, a severe mutation to the HGPRT is the lysineihand syndrome. So this component, if you're curious, feel free to Google that. The images aren't super pretty, which probably means that you're all Googling it right now. But in this case, this mutant has low residual catalytic activity. So instead of it being a deficiency, it's going to be really low activity. And so this is a hereditary component, and it's found on the X chromosome, which means that it's going to affect males only. And so it is super severe. So one of the other things is it can be quite lethal. And so it's not treatable, and it has severe side effects such as learning disabilities, motor disabilities, and hostile aggressive behaviors. One of the hallmarks of this is basically that, and this is why there aren't any pictures in there, people with this syndrome kind of in their aggression tend to chew on their fingernails, except they can't really, I don't want to say sense pain, but one of the things you'll notice is their fingers tend to get shorter over time because they basically chew on them without being able to see your faces. This gets odd, but they basically chew their fingers back over time. And so this is a terminal disease. And so we don't tend to see people with this disorder live for very long. And so it tells you that some people can be carriers of this. Not everyone has this disorder, but this is a severe mutation of that disorder. So it tells you that the ability to salvage purines is important. We also know that the ability to do that can have, next, we're going to start to think about pyrimidines. So pyrimidines are a not six carbon, but a 6-membered ring. And so it turns out that this pathway is way easier. Now, that shouldn't shock us as chemists, because when we think about the ability to make something that's 2 rings versus 1 ring, more likely than not, which I'm sure we will now find out that it's very unlikely and terrible things, I'm giving you all kinds of bad advice. But it's easier to make small components most of the time. And so pyrimidines are much easier. They just have 2 components to make this ring, carbonyl phosphate and aspartate. So these 2 molecules come together and create our ring system, and then we can go from there. So if we move to, I'm not doing a good job of slides today, I'm sorry. If we move to slide 57, pyrimidines are synthesized in 9 reaction steps, but the last 4 steps are the addition of the triphosphate. So if you remember back to the purines, it was 10 steps plus 2, plus later, it would have to likely be 4 steps to add the triphosphates. So 10 plus 2 is 12, plus 4 gives us somewhere on the order of 16 steps in order to make an active molecule, as opposed to 9 steps in order to create the pyrimidines. So you may also be asking yourself, are you required to memorize any of these things on slide 57? You are not. You do not need to memorize the de novo synthesis pathway. You do not need to memorize any other components of that. But it's important to think about the number of steps between the first pathway and the second pathway and the different avenues by which that occurs. So if we switch to slide 58. So the regulation of DNTPs. So DNTPs, the active form, like pretty much every other biological molecule that we've come across, we need to regulate the level of DNTPs. So if we look at the graphics on slide 58, we can see that there is a catalytic enzyme, ribonucleotide reductase, and this is going to regulate the levels of DNTP. So we know that we need the ability to regulate how many DNTP stores there are. We don't need too many or too few in any given shape, form, or fashion. So if we look at this graphic, we can see that the ATP and other molecules basically can self-regulate. We can see that this is a homodimer of a blue copy and a green copy. And so as we think about these, it starts to add, it tells you that we are going to have feedback loops here. So failure to regulate the DNTP pools leads to a higher rate of error in DNA synthesis, or that it takes a long time. So I want you to vaguely, in our memories, I know it was a long time ago, it feels like I haven't seen you in 100 years, but before exam 1, in chapter 22, I think, 22, we thought about what happened if we took away the option for all 4 DNTPs and we only gave it one option. It slows down DNA polymerization because it keeps trying to make the Watson and Crick base pairs. But if you don't ever get to using the other, it basically, I don't want to say gives up, but it basically shoves forward and then tries again. So if the pools of DNTPs are uneven, meaning you have way too much GTP or GTTP or GCTP or GDATP, whatever it is you have too much of, it's going to cause more and more errors in your DNA synthesis or repair or anything else. So if we can't regulate this using ribonucleotide reductase, we are going to have errors in the DNA. Those errors, if there still aren't re-levels, are going to be unrepairable as well. So we do know that we want to be able to have a feedback loop that tells us when we have too much of any one or the other, and to make sure that those pools are in an appropriate bound level. So if we move to slide 59, we want to convert the UMP, so the uracil monophosphate, to the TMP. So we know that the uracil and RNA, and so we would like to convert it back to TTP through thymidylate synthase. We've talked about thymidylate synthase a few months ago, I think, in class. And so if we look at this cycle, we can create the DUMP uses thymidylate synthase in order to create DTMP. So we have the addition of a methyl group using some of these cofactors that you see in the lower portions. But at this point, it's about the movement of the methyl group onto the cofactor, which is utilized in our thymidylate synthase. So this DTMP, so if we can't form that, we are going to have more errors. So thymidylate synthase is really important because there is a large pool of DUMP. So you'll notice this molecule at the top where it says F-dump. So we've talked about F-dump being a nucleotide, basically an analog that you can add, and we mentioned that it can be used as a cancer treatment. So for the next couple slides, basically the end of today's lecture, it's not very long, we're going to talk about how thymidylate synthase is a good cancer target. So cancer targets, we know their active job is that we need to be able to alter cellular synthesis. Cancer cells replicate quite quickly, so we know one hallmark of cancer is that the cells are over-replicating. Why they over-replicate can be for lots of reasons, such as too much of any one gene, not enough of another gene. There are a lot of ways that you can arrive at cancer. But if you can't make DTMP, you will not be able to replicate your DNA. If you can't replicate the DNA, the cell can't divide. So I don't want to say therefore. So if you can prevent this, then we can start to have the idea that this won't be functional. So on slide 60, thymidylate synthase and cancer. The goal of chemotherapy, most of the time, is to interfere selectively with the replication of cancerous cells. Now, there are new cancer treatments that target cancer cells for specific degradation. This is not that pathway. Yikes. I didn't realize you guys were looking at my creepy closet all day. So the drugs that function as TS pathway inhibitors, they bind in the active site. So the thing in this case is that we're going to affect cancer cells by preventing cell replication, by draining the TMP pool. If you take all of the water out of that pool is now going to have a hard time being useful. So in this case, if we look at these different molecules, we can see F-ura, which is 5-fluorouracil at the bottom, which salvage pathways can create F-dump. And once you create this, it's going to terminally add into the thymidylate synthase. When it does that, it blocks the active site. So now we have to make a new copy of that protein. So at the top, there's also another molecule. So this is AZT, or 3-azeto-2,3-deoxy. It looks like a DTMP, so a thymine monophosphate, but on the 3' we have an azide group. That azide group will prevent the addition into this chain. And so that azide group alone, which azide is N3, so that right there prevents the ability to add anything onto that. And so this too will functionally inhibit DNA synthesis or DNA replication. So if we look at slide 61, so thymidylate synthase, the structure for this protein was solved in 1991, which is just under 30 years next year. So this structure has been around for a long time. And so drug docking studies, which is basically where we take a protein structure and then add in small molecules and ask this question, does it fit in this pocket? Yeah. So if you can inhibit thymidylate synthase in cancer cells, it can lead to apoptosis. So there are lots of drugs that try to modulate into this pocket. And so you can see them in different inhibitors. So on the left side of slide 61, Ultima, Tomidux, and Thymidatac. Now, keep in mind that at some point, different drugs are used less or more, but all of these inhibit thymidylate synthase. When it does that, it's going to lead to apoptosis. So it's worth reminding ourselves that apoptosis is just cell death in this case. So when a cell dies, it undergoes apoptosis. You can have designed apoptosis where a cell naturally dies, it ends its lifespan, and then it does that. But if you can force a cancer cell to go into cell death, then that is advantageous. So Ryan asks, how does the drug distinguish between a cancer cell and the normal functional cell? So this is a really good question. And so the thing is, it doesn't. So we know, based on exclusive amounts of TV that I watch, or knowing cancer patients, that a lot of times their drugs make them all very sick. So the idea with thymidylate synthase is that cancer cells are rapidly dividing. So a hallmark of cancer cells is that they continually divide and they continue to replicate. So the idea is if you can, there are some drugs that just target specific cells. Thymidylate synthase inhibitors do not. They are found in all of the cells. But if you can actively inhibit cells that are rapidly dividing, and you can't take the drug for very long, but when it does this, then we can get them to stop dividing. When they stop dividing, then they can continue on to you can stop the drug. So this allows you to stop pseudo-selectively. So it will affect any cell that rapidly divides. By and large, in an adult body, the rapidly dividing cells are cells that are continually turning over, hair cells, skin cells. So some of these, and I don't remember if all of the TS inhibitors can affect hair and other things, but it doesn't selectively attack cancer cells. Cancer cells are more likely to be affected due to their high replication rates. And so if you stop their ability to replicate for a period of time, they can't replicate as fast, and then the cancers will, you can treat them in other methods, or that can stop cancer. Good question. So if we look at slide 62, the medically useful analogs, so some of these we have seen before. So FDUMP is one of those. So in the 1940s, 6-MP, which is 6-mercaptopurine, which is a purine molecule with a thiol at the top, and used to treat leukemia. And so there are a number of different pathways by which we can affect disorders by using analogs to DNA, whether it's the purine ring or pyrimidine ring or something else. And so many of these molecules are prodrugs. And so we talked about it last Monday, that prodrugs are molecules that must be metabolized. And so the metabolizing means basically that they have to be partially degraded in order to be most effective. So this is true. This is Florida, and so I can speak for myself, but I'm highly allergic to Florida. And so the allergy meds that I take are prodrugs that basically get degraded over time, and that allows them to work for 24 hours. And so a prodrug basically just means that the active molecule is only a part of the chemical that gets put into the drug. So you can have prodrugs, or you can have drugs where you ingest or consume the active form. So chapter 19 is actually quite short. So does anyone have any questions about Metabolism Bootcamp in general from any of the chapters, about gout, de novo synthesis, or salvage synthesis, or anything else? Mm-hmm. So the question is, how can you explain or asking about lysineihand syndrome? So in this case, lysineihand is it is a severe mutation to the hypoxyxanthine guanine phosphoryl ribosyltransferase. So HGPRT, if you look at slide 54, HGPRT is involved in the IMP to GMP conversion pathway. So if you look at slide 51, it is involved in the pathway. So on slide 51, the inosine monophosphate, in order to go from IMP to XMP to GMP, the HPGRT is one of the enzymes that is in that pathway. And so if you affect this pathway, so by turning that off, the xanthine oxidase, so the xanthine oxidase can create an irreversible component. So lysineihand syndrome has low residual catalytic activity. So typically in gout, you can get some level of turnover in this system. You just have more uric acid buildup. So in lysineihand syndrome, the purines, so the purine salvage enzyme basically tells you that you can no longer salvage purines and you have to make all of them. So in the lysineihand syndrome, it is super severe. It's basically a very, very severe gout. But typically gout gets worse as you get older because you start to get deposits over time. And then there are lots, you can have the gout deposits basically scraped out, and then they will return, but it gives you a chance to use lifestyle changes, dietary changes, or to use allopurinol. So lysineihand syndrome, the gout, the uric acid deposits start much, much earlier in life. Does that answer your question? Any other questions today? That is correct. In lysineihand syndrome, you cannot reuse purines, or it requires significant energy in order to recycle any of those. They do have to be synthesized. If you can't use the salvage pathway, everything must go through the de novo pathway. Does anyone have any other questions? That is all of the slides for this section. We will start the molecular cloning section. You can expect it to actually be a much longer lecture on Wednesday and through the rest of the semester. We will, just so that you can make sure you're prepared, there will be a variety of handouts, but there won't be any slides posted. I will drag this whiteboard over and then draw on that while we talk about it. My guess is we'll start at that top of that list and the top of the Jove videos. I don't know how far we'll get. It kind of depends on the level of questions and how the drawing on the board and the rest of that goes. As of this moment, if there aren't any more questions, then I'll hang out here for another second. Bioinformatics, there is a potential chance, but we will not be doing that through this forum. I am still working on the ability to create those types of exercises for you. We will talk about parts of bioinformatics in our molecular techniques components, but it will be quite different than what was planned at the beginning of the semester due to the fact that we cannot all meet in the same space. Other questions? There will be a final. Okay, so John asks, and it says it's unstable. Okay, so John asked if there will be any more slides. Not in the immediate future. There will be a handout that I will post, and I will try to work with that. So on Wednesday, my recommendation is to bring a piece of paper to wherever you sit, or any other way that you can take notes. I will draw on the board and try to go in that way. There is a handout that I would have given you in person, but we're not in people. So you can, in the new module called molecular cloning, or whatever it's called, there should be a handout that goes up sometime tomorrow by midday. But yeah, no more slides. Oh, Maggie, that's such a great question about what the final will be like. I have no idea. UNF has provided some new testing software that I'm going to webinar about. We will have one. Right now, the options are some version of a untimed take-home part and a timed part. All take-home, all timed. It will be run through Canvas. Canvas has some lockdown browsers where basically it tells you that you can't use Google. Hopefully I will provide much more information as we get closer. It will be during the time when it would have been, which I think is the Wednesday of finals week. So, any other questions? All right. Well, I'm going to let you guys go so you can, I'd say, go outside and enjoy the sunshine, but maybe you could do that 6 feet away from everybody else. Stay safe. I miss you all, and I will see you on Wednesday, or feel free to come to Zoom. I just kind of hang out in there by myself. And I will see you guys next week. No, on Wednesday. I'm sorry. Days of the week are hard. Bye, guys.